All right, integration by parts fun time here. We recall that the integral of u dv is equal to u times v minus the integral of v du. And if we can pick the right u and dv values from the beginning, then things will work out nicely. So we're going to let u equal something and dv equal something such that this right here is u times dv. Remember that the dx has to go with the du. Nope. The dx has to go with the dv at the beginning. And other than that, we want to make sure that whatever we pick for u differentiates nicely, and whatever we pick for dv integrates nicely. So remember that polynomials tend to integrate nice or differentiate nicely, right? Power rule brings the polynomial's exponent, in this case from 1, down to 0. So that's definitely a nice thing. Just like the last one that we did with x times the cosine of x, we let x equal u, because when you take the derivative, it just goes away. It turns into a 1. And then what about this e to the 2x? Is that a nice thing to integrate? Well, yeah. I mean, it doesn't get worse at the very least. It doesn't get better either. It's just e to the 2x stays e to the 2x. We have to remember the chain rule, of course, but other than that, there's nothing too fancy going on here. So du equals dx, and v equals 1/2 e to the 2x. The biggest mistake that people make here is they'll think they're differentiating here. They'll put a 2 here. They'll feel very proud of themselves that they're remembering the chain rule, and they'll put a 2 there, but then there's, wait a second, you're going backwards, so it should be a 1/2. I guess the other big mistake might be that you just completely ignore the 2 altogether and just put 1 e to the 2x, but that's equally bad. Anyway, so our integral of u dv is equal to u times v, so x times 1/2 e to the 2x, u times v, minus the integral of v du. So 1/2 e to the 2x times dx. All right, so this integral is easier than the original integral because instead of an x, it's now a 1/2. And who cares about constants, right? These coefficients could just get pulled out. So we've got 1/2 x e to the 2x for our first term, minus 1/2 times the integral of e to the 2x dx. But we just did the integral of e to the 2x dx. It was 1/2 e to the 2x. So we'll put a 1/2 e to the 2x here. And we'll put a plus c in here, and that's our answer. A lot of times in these sorts of problems, we like to factor out stuff. In this case, we can factor out a 1/2, and we can also factor out an e to the 2x. And then what's left is just a single x in the first term, and then a 1/2 in the second term. And then there's a plus c. And that's a nice final answer, I think. The line before that is an acceptable final answer as well, but a lot of times those multiple choice questions will have it factored out. You could even do something like this if you wanted to factor out another 1/2 and have this be 1/4 e to the 2x times 2x minus 1. If you wanted to get all the fractions in one place, that's fine. Whatever. It's all the same. All right, cool. So on the next problem, we're going to have a little bit of trouble doing the same general rule, right? Where we said, oh, whatever the polynomial is, we're going to let it equal u. Because take a look over here. If we let u equal x squared, then sure, du equals 2x dx, and 2x is simpler than x squared. But the problem with that is then we let dv equal the natural log of x dx, and that's something we don't know how to take the antiderivative of yet. Dun, dun, dun. So yeah, maybe we shouldn't put the natural log of x over here because we don't know how to, I don't know how to delete this even. Let's see, let's try that again. Yeah, there we go. We don't know how to integrate that, but we definitely know how to differentiate the natural log of x. So we'll put the x squared over here. Okay, so yeah, when we integrate this, it will get more complicated for sure. The exponent will go from 2 up to 3. Which generally makes us a little sad. But it's worth it, because what happens over here is this transcendental natural log of x, the transcendental function, goes away, right? And we just get this rational function as our answer. The derivative of the natural log of x is the simple 1 over x. So while at first glance it might seem a little problematic, this is going to combine very nicely. So going back to what I said earlier, if you're not sure what to let u equal and let dv equal, just try something and see where the formula takes you. It might take you to a dead end. It might take you to where you need to go. So just try something and play around with it. The best way to learn math is by doing math. Some famous person said that once. I forget who. Anyway, u times v is natural log of x times 1/3 x cubed minus the integral of v du. V, and this is where we see, oh, that's actually very nice, right? Because du is 1 over x dx. And these guys combine really nicely, right? The x cubed over x reduces. So this is a much simpler integral because it's just x squared, right? In fact, coincidentally, we just integrated x squared. So we can just do the same one again. So we get 1/3 x cubed natural log of x minus 1/3 times 1/3 x cubed plus c. And again, that could be your final answer, but we like to factor when we can. So 1/3 x cubed is in both of the terms. And then what's left is natural log of x minus 1/3 and then plus c. And I like that as a final answer. It's a good one. But again, you can do the same thing we talked about last time, where you could factor out another 1/3 and get 1/9 x cubed, and then have 3 natural log of x minus 1. And that's fine too, but whatever makes you happy, right? So if it's a form that is useful, or if you're just tired of the problem, whatever, it's like, if it's right, it's right. So don't forget that we can always check these with integration. I'm not going to do that in this video because then the videos would get way too long, but we can always take any answer that we get, take the derivative of it, and make sure that it takes us back to the original integrand. Alrighty, moving right along, we got a few more. I think I'll do number 3 on this video, and then we'll do number 4. We'll learn the tabular method on the next video. So take a look at this. We've got x squared, and we've got a sine of x over 3. All right, so try something. We're going to let u equal something and dv equal something. Here's an idea. You try something and see where it takes you before you watch me do it. Because I know how to do it, but you should practice it so that you can see where it takes you. But I'll go ahead and do it now that I'm assuming you guys have paused the video and done it. And we're going to pick u equals x squared because that differentiates to something simpler, and dv is going to be sine of x over 3 dx because that does integrate into something that's not messier. So we'll see that du equals 2x dx, and v equals, well, let's see, the cosine should be negative, and it should be not a 1/3 in front, but a 3 in front because we're integrating. So again, same concept, right? You can take the derivative of this and make sure it takes you back to here, which it will. So that's going to be a good start for this. We're going to take u times v, which is x squared times negative 3 cosine of x over 3 minus the integral of v du. All right, so let's see what we can do here. We're going to clean this up. We're going to put a negative 3 out front, x squared cosine of x over 3. Minus a negative is plus. The 3 and the 2 multiply to get 6. And now we have the integral of cosine of x over 3 times x, or I like it better like this, x cosine of x over 3 dx. All right, so now we're looking at this and we're saying, well, this integral is definitely better than this integral, but it's still a little messy. If you think back to our very first example, oh, here it is, the integral of x times the cosine of x dx, that's essentially the same thing we've got going on right here. The integral of x times the cosine of, not x, but x over 3, so basically the same thing. So what do? We integrate by parts again. So now we're going to let u equal, it's no longer x, x squared, it's going to be x. So we're going to do x, and then dv clearly will be cosine of x over 3 dx. and du equals dx again, like we've seen in other problems. V is going to equal 3 sine of x over 3. So when we keep on going with this, let's not forget about this first term that's been taken out of the integral, so that's still part of our answer. Plus 6 times, let's remember parentheses here, so that whole uv minus integral of v du is going to be multiplied by 6, so that parentheses is important. So now our u value is x, and our v value is 3 sine of x over 3. Then we're going to subtract the integral of v du. That's 3 sine of x, x over 3, times dx. All right, close that parentheses there. So we can have negative 3x squared cosine of x over 3 plus 18x times the sine of x over 3 minus 18. And let's see, we've got this integral. I'll go ahead and write it one more time. The integral of the sine of x over 3 dx. Well, that integral is something we did at the very beginning of the problem, so we definitely know how to do that. We'll get negative 3x squared cosine of x over 3 plus 18x sine of x over 3 minus 18 times negative 3, so that's going to be, I don't know, 54, I guess, I think, yeah. Cosine of x over 3. And then we have a plus c. And that is a crazy answer. But it is the right answer. It's kind of interesting. It's got this quadratic feel to it. We've got an x squared term and an x term and a constant term, except for it's not really constant because it also has a trig thing in it too. Notice that it alternates back and forth between cosines and sines. That's not at all uncommon with these sorts of problems. All right, so I mentioned we'll use the tabular method for the next one, but take a look at the next one. You can imagine that we could try to do the next problem using the same method we did here, right? Since this was x squared, we had to do integration by parts 2 times. Since this is x to the 4th, we're going to have to do integration by parts 4 times, which sounds terrible. So that's where the tabular method comes into play. So it's a nice shortcut. So on the next video, we'll take a look at how that works.